In this example, we're again going to use the Biot-Savart law to look at another geometry that displays enough symmetry and is simple enough in terms of the calculation to solve analytically. We don't have to solve it numerically, computationally. So as it states here, we're looking at a wire carrying a current shaped into a circle. Now that we don't have half an arc, we have a complete circle. And notice that we're looking at a point on the x-axis to solve for the B field at this point here. And the x-axis is perpendicular to the plane of the loop and passes through the center. So what we are looking at is the B field calculation due to each of these IDLs, which note they're still tangent to the r hat vector. The geometry is a little, I think, more difficult to let your eyes see the perspective on, but hopefully you can see it, the cone that the IDLs are going to sweep out with the r hat vector. And what we're looking at first is just the B field contribution from the top of the page. So let me put a T here and top here. So make sure you get the notations as to where they are coming from. Now, from the IDL at the top of the page, we will do IDL cross r hat, where we have to imagine, I didn't want to make the page too messy, that we're going to actually translate the IDL cross r hat to the point in space where the B field is. We're going to do IDL cross r hat. It will be perpendicular, right? So the B field, let me erase it for a second. The B field that I'm showing will be perpendicular to the plane that has r hat and IDL in it. So that arrow here is the arrow I have shown down here. And that's from the IDL component at the top. Then by symmetry, when we go directly to the other side, we have our IDL at the bottom. Hopefully you can see that the B field contribution from the bottom DL is down here. And notice when we're going to use Biot-Savart law to problem solve the problem, we look at the cross product first. Here we have sine of 90 degrees. So again, it's a little hard to see the 90 degrees. I'm going to zoom in here, but there's your 90 degrees between the IDL that's tangent and the r hat that goes radially in, and it's the same down here. It's tangent, and the r hat goes directly to the point, so it's kind of an angled plane we're looking at. Again, hopefully you see the perspective, but we can talk more about it in class as well. So the r hat is a unit vector, so that's why we have 1 here. And cosine of 90 degrees is 1. IDL over r squared, so now we're down here. We're going to integrate to get the total B field, so that's why my limits of integration go from 0 to B total. And here I did leave it in terms of L. I did not go back to theta since we're just going all the way around the circle. It was the easiest to show. You could put it in terms of r d theta, though, and would get the same answer. So we have the introduction of the sine theta. This is important for you to note that this sine theta, let me get it in a different color, this sine theta does not come from the cross product. So please add to your notes here, not from, and hopefully you can write it a little more neatly than what I'm able to, cross product. So not from cross product. Okay. So please make sure you get that into your notes. That sine theta comes from the fact that we're only left with the x component of the entire B field from the IDL because the y components cancel out. So again, make sure you have a complete annotation into your notes to show that the by's cancel out and we're only left with the bx's, and then everything kind of falls into place. We get the current remains constant, comes out of the integral. The r also remains constant, but notice now the r in our Biot-Savart law is not the capital R for the circle. That's kind of important. The little r in the Biot-Savart law is this r here, or this little r here. So that little r is the hypotenuse of that right triangle. So here's the capital R that's part of that loop. So the little r remains constant. It still comes out of the integral, but here you go. Here's where we have to note that the little r is the hypotenuse, and that's why it's going to be opposite on hypotenuse, where my angle theta is shown here. And you have to look at the geometry to see that the angle theta here is the same as the angle theta here, but it definitely is if you follow the geometry. That is definitely the case. We have 90 degrees here. We have theta plus 90 degrees plus, if you want to call it phi, down in here will equal 180, so that means theta has to be the same theta up top. And if you take your time, you look at the cancellation that occurs. We lose the 2 pi, the 4 pi, and are left with a 2. And when we make the substitution for the little r, we could simplify further, but I just left it in your notes, and you can just leave it in your notes with the little r cubed in the bottom. But really, since we would be looking for b as a function of x, if I had room to do more algebra, I would simply substitute that in for the r cubed, and then you have everything in terms of x. So we could use this expression to find the b field anywhere on the x-axis. So there you have it. There's a little bit to it, but believe it or not, this is about as simple as we can do with the Biot-Savart law in terms of the geometries. That's about it. We'll look in another lesson as to how complicated it gets when the geometries don't display this type of symmetry.